Today we are going to use Laplace transform to solve a system of ordinary differential equation. And we know once we talk about Laplace to use, we have to get initial value, right? Okay. So let us remember what is the linear system. This is the linear system of differential equation of first order, of course. The first derivative in one side and the rest in the other side. We remember we have here, if we differentiate it with respect to t, if we have a function of t, okay, we will call this one non-homogeneous. If we don't have a function of the independent variable, whatever it is, t or x, we call it homogeneous differential equation, system of differential equation. Okay, so the matrix A is a coefficient of y1, y2, yn, the dependent variable, right? And the vector, the column vector y is the dependent variable. And if we have a function of t in each one of these, so this is the column of the non-homogeneous part, right? Let's see how we can solve a system of homogeneous first. Okay. So as we said, we take the coefficient matrix, we get the eigenvalues of the matrix A. Okay, if it is n by n matrix, we will have n eigenvalues. And of course, we will have n eigenvectors. Each eigenvalues has a eigenvectors, x. How we can get the eigenvalues and the eigenvectors? You know how to do this one. Now let's go for using the Laplace transform, okay? And as I said, we should have initial value. Laplace transform is the process to transfer the differential equation into algebraic equation. Once we have the algebraic equation, it is easy to solve up to the Laplace, right? And we get the Laplace inverse, we get the dependent variable as a function of the independent variables, right? This is the way we know when we use Laplace transform to solve ordinary differential equation. This is the Laplace table for most of the function, right? And here is some rules to have a Laplace transform for the first derivative, for the second derivative, and also for n derivative. This is why I'm saying we should have initial value to use Laplace, because if we have a differential equation, we have a first derivative, second derivative, and n derivative, and I see the Laplace for the first derivative must have initial value at f or y at 0, right? If we have a second derivative or second ordinary differential equation, we should have two initial conditions, one for the dependent variable and one for the derivative of the dependent variable, right? At the independent variable equal to 0. This is why I'm saying we cannot use Laplace unless we have initial value. Also, we have this form. If we have a function multiplied by t, we can forget about the t for a little while and find the Laplace for f of t and differentiate it with respect to the s and multiply it by minus. This is how to get the Laplace. And if we have Laplace inverse for a derivative for some function of s, the Laplace inverse will be minus t times f of t for the original f of s, not f dash. Also, if we have a function multiplied by e to the at, we forget about e to the at for a little while and find the Laplace transform for f of t and replace s by s minus a, because we know the Laplace f of t is a function of s. If f of t multiplied by e to the at, we get f of s and replace s by s minus a. Also, Today, we're adding a function, well-known function in electrical engineering, okay, and in wave in general. It's called unit step function or heave side function, at the name used in MATLAB. Okay, this is the definition of unit step function. U of t minus a, and a is a constant, is 0 before the a, and it is 1 after a. Okay, so this is a graph. If a is 0, it means u of t minus 0, it will be u of t, will be 0 at t less than a, so nothing here, it is 0. After 0, it will be 1. In general, if I have ut minus a, I will start from a to give the value of the unit step function equal to 1. Before the a, it is 0. Okay. What is the point of studying unit step function? Unit step function action on wave has two actions. One of them is like switch on, switch off, or cutting a wave. If I multiply any wave represented by the function f of t, whatever, 5 sine t, for example, and I would like to cut this wave and let it start from 2, not from 0. I have to multiply this f of t by the unit step function minus the cut I would like to do. Okay. The other action, no, I don't like to cut the wave. I would like to shift the wave. Shifted by 2 units in the positive side of the independent variable, right? So what you are going to do, you replace t by t minus the shift you would like to do, and multiply by the unit step function of t minus the shift you would like to do. It's very important to know why you are doing so. Okay. Section B, you can call it switch it off and on. Okay. So if I would like to take a period of time from 0 to 2, so I will have to cut this part, right? So I have f of t minus, yes, f of t multiplied by ut minus 2. Okay. So we know what is the action of the unit step function on any wave. Okay. What is the Laplace transform for the unit step function? The general form of Laplace transform is you get the function you would like to have the Laplace transform for and multiply it by e to the minus st and integrate from 0 to infinity. I know the unit step function t minus a has 0 value before a. So I have to start to integrate from a to infinity, right? And it is 1 from a to infinity. So I am going to integrate 1 multiplied by e to the minus st from a to infinity. The integration of e to the minus st is e to the minus st over minus s. When t equal infinity, infinity will be multiplied by minus, e to the minus infinity is 0. Minus the value at t equal to a, minus minus will be plus. Ft equal to a, I have e to the minus sa over s. This is the Laplace transform for the unit step function. Okay. I need it? Yes, I need it when I'm going to solve some question in electrical engineering. Okay. This is a representation of second shifting theorem, or time shifting, as you call it. So I would like to shift the wave represented by f of t and start from a. So I replace t by t minus a and multiply it by the unit step function t minus the shift. Okay, so it will be 0. And the unit step function will be 1 after a. So 1 will be multiplied by this one. Okay. Fine. What is the Laplace transform for this shifting after I shift the wave? It is the same as e to the minus as multiplied by the Laplace transform for the original f of t, for the original wave. Catch it? Okay, that's good. What about the Laplace inverse if I have e to the minus as f of s? It will be the opposite side. So you have the original function f of t and replace t by t minus a and multiplied by the unit step function t minus a. Okay, but this is the main point. Laplace transform for the wave after shifting into a is exactly e to the minus as multiplied by the the Laplace transform for the original wave represented by f of t. Okay, we have this electrical network. We have two loops. Okay, we have different current in each loop, but there are something in common between the two loops, like this resistance. So this resistance will be involved in the first loop and also will be involved in the second loop. But the current, when it's involved in the I2 loop, it will have a current I2 minus I1. But when it is involved in the loop of I1, it will have the current I1 minus I2. This is the main point here, right? Okay. Now, how we can write the mathematical modeling representing this network? Yes, I'll go to the Kirchhoff law and I'm writing equation for each loop like this. Okay. Let's go for the loop having the source of the power, right? He give me the source of power is what? 100 volt. But he's not leaving this working for forever. He left it work only for half second. Okay. And you have no current when you start and no charge in the capacitor when you charge if you have a capacitor, right? But here I'm lucky I don't have a capacitor, so I don't have any problem with this one. Okay. So this is the first coil here. So the conductance here is what? 0.8. So I have the current here will be L di by dt. L is 0.8. di by dt is I1 dash, and this I here is I1. Okay. And this is a common between the two loops. As I said, when you go for this loop, you will have it as resistance IR. So R is 1, and I have I1 minus I2 plus the other resistance, this one, 1.4. What is the current? I1. Okay. Equal to what? Equal to the input. The input is 100. Okay. But it's not working forever. It's working for half second. So I will have this 100. Okay. When it starts, minus, I switch off after half a second. So I have to multiply this 100 by u of t minus half. Again, the source here is DC, of course, because it's 100, no sine function, no cosine function. So it is not alternating. It is DC, direct current. How to write the input? The input is 100. That's fine. I leave it 100 if it's working forever. But if it's switched off after half an hour, so I have to cut from this 100 into the time half second. So I have to multiply the 100 by u of t minus half. Okay. Now let's go for the upper loop. The current in this loop is I2. This is L di 2 by dt. L is 1, so I1, I2 dash. Plus, this is in common also. It have 1 as a normal resistance times I. I in this case, it will be the main current I2 minus I1. No source here, so it will be 0. Fine. Now I have two differential equation. I can write it down as a system of differential equation. I will have I1 dash in one side and the rest will be in the second side, and I2 in one side and the rest will be in the other side. Okay. And I'm writing the initial condition as I1 0 at 0 and I2 is 0 at 0. Okay, good. How to solve it? I have to take Laplace transform for the first one and the second one, right? Okay. Now, in the first one, I divided by 0.8. So when I divided by 0.8, I have 1.4 over 1.8. So it will give you this one. 100 over 0.8, you have 125. Okay. This is the first one. The second one, okay, I'm just adding. I'm just opening this one, I2 minus I1 equal to 0. So take Laplace for the first one. I have no problem to have the Laplace for the first derivative, okay, of I1. And Laplace for I1 is the Laplace for I1 minus 125 Laplace for I2. And what is the Laplace inverse for the 1? It's 1 over S. Yes, this is the new stuff we got it here today. The Laplace for the unit step function t minus a is e to the minus as over s. So a is half, so minus s times half over s. Okay, Laplace transform for the second one, here it is. Now, I cannot get Laplace inverse and for the two variables, I1 and I2. So I have to solve this two algebraic equation and substitute by I1 in terms of I2 in one of them, okay, or I2 in terms of I1 in one of them. At least I will have I1 in one side, and they have a function of f of s on the other side, also the same as I2. Now I'm looking for the inverse Laplace for this one. This one multiplied by 1, I have no problem, and I can use the partial fraction to have Laplace inverse for this one. What about if I multiply by e to the minus s a? I said, yes, here is the formula. If I multiply by e to the minus a, forget about e to the minus as for y, right? And look at the f of s itself without e to the minus as, and find the Laplace inverse of this one. Okay, so you get f of t. Now what you are going to do, replace t by t minus a and multiply by t by unit step function of t minus a. This is what happened here, right? I got the Laplace inverse for 125 over s times s plus half times s plus 7 over 2, right? And then I replace ht by t minus half, right? Okay. So I get the Laplace inverse for I1 of s, I capital 1 of s. I get the current in the first loop and I get the current in the second loop. Catch it? Okay. We know how to find the solution of system of differential equation. What about if we have initial condition? You just add the initial condition over here, right? Okay. Now, let's do it by MATLAB. Stems. let's have any one of this question and we can solve it by MATLAB. Okay. Sims P Y, you call it Y1, okay. Y2, okay, semicolon. Yes, the command is desolve, okay. What is the first equation? dy1. This is how to write the first derivative, dy1 minus equal minus y1 minus y2. This is the first question, the first equation, comma, the second one, y2 dash. How to write y2 dash? It is dy2 equal to, I have to put, okay, dy2 equal to y1 minus y2, y1 minus y2, okay, finish this one. Now I can write the initial condition. What is the initial condition? y1 of 0 equal to what? Equal 0, and y2 dash, sorry, y2 at 0, sorry, equal to what? Equal to 1. How to write the MATLAB command to solve this one. Let's go and see. Yes, we have a problem with symbols y1 and y2. So I can replace y1 by x, and I can replace y2 by y. So I can call this one x, I call this one y. So this is, I call it x. This is still x. This is y. X. I call y1 x and I call y2 y. So, okay. Let's go now. Yeah, I have a problem with sims. Okay. Control C. Yes. What's the problem here? Do we have a problem with the... Okay. You know, so what's the problem here? Okay, expect differential instead. Okay. Do we have to write equal like that in this version? Do you see what's the problem here? I see. I see now. We have a bracket, open, not closed, right? I have a problem.
Doctor, also for the last term, it's
this is
y
one.
0.
Yeah. Like sorry, not like that. Like this.
Yes.
No, still having problem with this one. So let's stop recording now. Okay.